video we're going to talk about the basic fundamentals of heat transfer and just some of the basic formulas that are used to calculate how much heat is transferring from one medium to another. For example, the outdoors through a house roof or exterior wall into the interior space of the house. The units that are used for thermal energy is the units of British thermal units, abbreviated as BTUs. Just like flow could be in units of GPM, or units of length can be in inches or feet. When we talk about thermal energy, the units that are used to represent that thermal energy is BTUs. Now, once you take that energy of 1 BTU and you apply a rate to that energy, right? So we can apply a certain rate of change of that energy. We do that by the rate of hours. So the abbreviation for that would just be BTU-H, which stands for BTUs per hour. Another term that we do is, which is probably very common to hear, is 1 ton, which is the equivalent of 12,000 BTUs per hour. And another common term that is used is 1 MBH, which is equivalent to 1,000 BTUs per hour. So you don't want to confuse that with like a megabyte, which is represented as 1 million bytes. So when we talk about thermal units, the MBH represents 1,000. Okay, so you don't want to confuse that with, let's say, 1,000 bytes, which is kilobytes. So just to clarify that point. Now, what is a BTU? What does that actually mean? Okay, it is actually the amount of heat that is needed to raise 1 pound of water by 1 degree Fahrenheit. So if we have water which weighs at about 8.33 pounds per gallon, that just means that you need 8.33 BTUs to raise that 1 gallon of water 1 degree Fahrenheit. Now, where did this 1 ton unit come from? What does that represent? So a ton is equivalent of 2,000 pounds. Okay, so 1 ton of ice being melted within a 24-hour period is actually the equivalent of 1 ton. So we'll just do a quick example just to show this point. Okay, so if you look at the chart here, okay, we have temperature on the first column, density in the middle, and the weight on the right side. This point here is the freezing point, which is 32 degrees. This point here is actually the point of highest density. Okay, which is right here, density column. And these are just different temperatures as the temperature increases. So from this point on, the density is actually decreasing. Okay, and also this way it's actually decreasing as well. So for this example, we're going to try to figure out what is the volume of 2,000 pounds of ice. So to do that, we look at the density of water at freezing, 32, and that's going to be 62.416 pounds per cubic feet. And 1 ton is 2,000 pounds. So this cancels out with this, and you're left with 32 cubic feet. And in a cube, one side, if it's denoted by x, you have x cubed is equal to 32 feet cubed, which is then going to be 32 raised to the 1/3 power, and that's going to equal 3.17 feet. So 1 ton of ice, or 2,000 pounds of ice, is approximately a cube that is 3 feet in length. Okay, so 1 ton is the amount of heat required to melt that block of ice that is approximately 3 feet in dimension on all sides within a 24-hour period, and that heat is 12,000 BTUs per hour. So that's what a ton is representing. Okay, another concept I wanted to mention is dry bulb temperature and wet bulb temperature. Now, dry bulb temperature is generally what people are referring to when they say, the outdoor temperature is, for example, 50 degrees Fahrenheit. It just means the temperature of the air. Okay. Now, wet bulb temperature is the temperature that a thermometer would be reading if it was wrapped with a cloth. So in this picture here, it would be this, that is sitting in some water, which means that this cloth here that's wrapped around this thermometer would be wet, and the temperature of that moisture is the wet bulb temperature. So the relationship between the dry bulb and wet bulb temperature is that, for a given dry bulb temperature of the air, as the humidity levels rise, the wet bulb temperature would rise. And as the humidity temperature drops, the wet bulb temperature would drop. Another way to think about wet bulb temperature is, or to understand the concept of wet bulb temperature is, if you are outdoors and you're sweating, the temperature of that sweat on your skin in that air is the wet bulb temperature. So as you know, if it's less humid outside, your sweat would feel cooler than if it was more humid. And we're gonna look at the exact relationship between the dry bulb temperature, the wet bulb temperature, and the amount of humidity in the air when we look at a psychrometric chart in later videos. Okay, now heat could transfer in different ways, and the 3 main ways they will transfer is by conduction, radiation, and convection. So this diagram is kind of a representation of what those different types of heat transfer represents. Conduction is when heat is transferred basically through a solid object. So it can be from this pot traveling through the metal in the handle to your hand. So the conduction is happening through the metal. Okay? And if you look at the picture on the right, the conduction is actually through the material, which in this case is just the ground. The heat is just transferring through this ground by conduction. Okay? And the definition is conduction, heat transfers heat via direct molecular collision. Or basically in a solid object, the molecules in the object are basically vibrating because the thermal energy is high in the hotter areas, and it transfers it to the lower kinetic energy areas, or the colder areas of that material. Okay, so the higher speed particles will collide with lower speed particles. These lower speed particles will increase in kinetic energy. Okay, the next form of heat transfer is by radiation. Okay, so it's basically the way the sun will transmit heat to the earth. It basically just travels through electromagnetic waves that is traveling through, for instance, space, and then hitting the ground and heating up the ground. Another way is, in this picture on the left, the radiation is just traveling through the air, hitting the pot, and heating the pot up. Definition is, in this case, thermal radiation generates from the emission of electromagnetic waves. These waves carry the energy away from the emitting object. Radiation occurs through a vacuum or any transparent medium, either solid or fluid. Okay, for instance, it could be the sun's rays going through a window into a house. Thermal radiation is the direct result of random movements of atoms and molecules in matter. Movement of the charged protons and electrons results in the emission of electromagnetic radiation. So everything actually emits radiation. Any object that is hot can emit radiation to an object that is surrounding it. Okay, now the third way of heat transfers is by convection. Okay, convection is basically heat transferring through a fluid. For instance, water, as in the picture on the left, or through air, which is also a fluid, as in the picture on the right. So that's convection. Okay, and the definition here is when a fluid such as air or a liquid is heated and then travels away from the source, it carries the thermal energy along. This type of heat transfer is called convection. The fluid above a hot surface expands, okay, which becomes less dense, and less dense rises. At the molecular level, the molecules expand upon introduction of thermal energy. So as it expands, the volume is actually increasing, and the density, formula of density is mass over volume. So as the volume increases, the density decreases. So as the density decreases, okay, so let's go back to this. As temperature of the given fluid mass increases, the volume of the fluid must increase by same factor. This effect on the fluid causes displacement. As the immediate hot air rises, it pushes denser, colder air down. This series of events represents how convection currents are formed. The equation for convection rate is calculated as Q is equal to HA delta T, where Q is the heat transfer rate in BTUs per hour, H is the convection heat transfer coefficient, A is the exposed area, and delta T is the temperature difference. We don't really need to be too concerned with this formula though when we calculate how much total heat is being produced in a space when calculating HVAC unit or an air conditioning unit. So you don't really need to be too concerned with this formula, but I still wanted to just show it to you just so that you understand what the formula is. Okay, so I'm going to now go over some of the formulas that are used to calculate the conduction rate of heat transfer through a material. And the formula that's used to calculate that heat transfer rate would be this formula here. Now, all the other formulas below that, which is here and here, all are derived from this first formula. And I'm going to run through how those are derived a little bit later on in this video. So, in this example, I'm going to create a wall here that could represent, let's say, the exterior wall of a house. And the outside temperature would be, let's say for this example, 95F, and the indoor temperature is 70F. The area that's plugged into that formula would be the area that the heat is being transferred across, or the Q. And that area is this area here. The S in the formula, which represents the thickness, is the thickness of the material that we're calculating the heat transfer across, and that's going to be this right here. So as you can tell, as the length increases, then the denominator would increase, which would lower the Q, which makes sense, right? The longer the material is, the lower the heat transfer rate across that material, with all else things held constant. And the K value in that formula is the thermal conductivity of the material, which is specific to the actual material that you're considering. Or it can be an assembly. So you can have, for example, an assembly that is like this, where you can have, a wood frame with insulation between the wood studs, and then you could have a continuous insulation with some other layers of material on top of that. So this whole thing could be represented as an equivalent K factor. So it could just be a single material, or it could be an assembly that will have an equivalent K factor. So in that case, we just consider what that K factor will be and plug that into the formula. Okay. And what I'm going to do is now plug in the values into the formula. So let's say K is, in this example, I'm going to just make it up as 50. The S, let's just call that 2 feet. And the area, let's make that 50 square feet. And plug it all into the formula. So Q will equal K, in this case 50, and putting in the units, it's BTUs over hour times Fahrenheit times feet squared over feet. Now this whole number is divided by S, which is in feet. So to rearrange this formula with the feet, dividing across this number here, right, will give you feet would basically move up here. So I'm going to delete this, and if it moves up here, it gets canceled out, and now you're just left with that. Now this is multiplied by the area, which is 50 square feet in this example, and then delta T. Delta T just means the temperature difference between the higher temperature and the lower temperature. So in this case, it's 95 minus 70, which is 25 F. Now all this equals to 50 times 50 times 25. Okay, now when you multiply this out, it'll come out to 62,500. And the units would be, this square feet will cancel out with this, the Fahrenheits will cancel out, and you're left with BTUs per hour. Another way to write that out is just 62,500 BTUH. It represents the same thing. And that actually checks out because Q is in units of BTUs per hour. So we know that, both sides of the equation, they have the same unit, so everything works out. Okay, now to get to this bottom equation, we're going to have to look at something called resistance, okay? And resistance is just S over K. And if you look at the top formula, we can rearrange this formula here to be like this: 1 over R, A delta T, because R is equivalent to S over K. So if you take the reciprocal of S over K, you get K over S. So these two things are the same thing. Now if we rearrange this, we get at that. Okay, where it's just delta T over A multiplied by A divided by R. Now the R is the reciprocal of U. Okay? and that's just a relationship between U and R. Okay, the U factor. And the U factor is in these units here. So if we plug in to this formula, U, basically the R by U, we're going to get delta T over 1 over U times A. Or, in other words, this is equal to U delta T times A. And that's how you get this formula. Okay, to calculate the heat transfer from radiation, from the sun into a space such as, an office, a house, or any other type of building, the formula that we use is right here. Q is equal to ASC times SCL. The SC stands for the Shading coefficient, okay, and the SCL stands for the solar cooling load. Now that is actually dependent on time because the sun's position for a certain area on the earth is all dependent on what time it is, and depending on that, that SCL value will vary. Sometimes the values aren't given in shading coefficient. Sometimes the value is given in something called SHGC, which is the solar heat gain coefficient. And just to do the conversion between the two, you use this formula here, where SC multiplied by 0.87 is the solar heat gain coefficient. So, for example, if you look at a window, sometimes you'll see a tag on it. Okay, right here, such as this one here. For a double hung window, they're going to give you different values. So here they give you a U value because you have conduction that is occurring across the window, which is based on whether there's a temperature difference between the two sides of the window. And they'll give you this solar heat gain coefficient. Okay. Sometimes it might be in SC as a shading coefficient, and you can use this formula here again just to make that conversion. Okay. So to get the value for this right here, solar cooling load, or in other words, it could be the solar heat gain factor. Don't confuse that with solar heat gain coefficient. Okay, now to get the solar heat gain factor, there's tables that are published that gives you the different values of the solar heat gain factor depending on where you are located on the earth. In this example, it's 40 degrees north latitude. Okay, and the reason I picked 40 degrees north latitude is because I'm from New York City when I'm making this video, and New York City latitude is 40.73 and the longitude is 73.9. And if you look at a picture of the earth, latitude are the lines that go horizontally, okay, this way, and longitude are the lines that go up and down this way. A good way to memorize it is latitude starts with 3 letters, LAT, that rhymes with fat. And when you're talking about something that's fat, you're talking about the circumference of that object. So that's just one way to help you remember, which direction latitude is and which direction longitude is. Now, going back to this table, you can see that, based on the date, here it's January 21, February 21, and March 21. And also depending on the time, the solar heat gain factor will vary depending on the orientation as well. So here's north, east, south, west. So if I go back to this picture of the earth, north is here, east, south, west. Okay, and the Earth is rotating in this direction here, and the sun, let's just put it right here. Okay, this is the sun. So looking at this table, the at noon, which is this 12-hour mark here, is the time of day that the sun is at the highest point at a particular location on the Earth. So in this example where we're using, let's say, the location of New York City, which is right around here, okay, the sun, if it is at the highest point, is going to be directly facing into the south side of a building, for example. All right, and that means that if we look across this point right here, January 21, at 12, which represents noon, or the highest point the sun will be at that particular location, you're going to see in this column here, the south, that the number is 254 for the solar heat gain factor. And if you look here, right, that's the highest value on the south side. It occurs at noon, and that's the value at every other day. So for example, February 21, if you look across the noon line and south, it's 241. Against that's the highest value, and the same with March 21. That is going to be the highest value among all these other values here. So the sun is representing the area that gives you the most solar heat gain, okay, and which occurs at noon in New York City. Another thing is, you might have heard the saying, the sun rises in the east and sets in the west. Okay, so if that's the case, that's also confirmed in this table. So if you look at the column for east, you can see early in the morning it's high, and as you go throughout the day, the values drop. And if you go to the west, right, where the sun is, it rises in the east, sets in the west, that means during the nighttime, the value will increase for the west, and we see that here. As the time gets later, the value increases, okay, on the west side. Okay, so let's do a quick example of calculating the heat transfer across a window. And in this case, the window will have these properties here. And let's say the window has an area of, I'm just making this up, let's say 10 square feet. And let's consider the time to be 9 a.m. and the window is on the south side. Okay, so you have north, east, south, west, and the window, so the building is here and the window is here. Okay, so we're going to use this formula here to calculate the heat transfer rate from the solar radiation through this window. Okay, we're going to first use this value for solar heat gain coefficient, 0.36. What we need is the shading coefficient, the SC value. So we have to do the conversion using this formula. So that's going to be SC is equal to solar heat gain coefficient for this window is 0.36 divided by 0.87, and that will give us 0.41. Next, we need to get the solar cooling load, or the solar heat gain factor, from the table at 9 a.m. on the south side. So let's say it's occurring on January 21st, okay? So this one right here. And at 9 o'clock is right there, and south is going to be 160. So it's going to be this value here that we're going to be using. So 160. So we're going to go back here, and this is going to be 160. Okay. Now we're going to plug all this in. Q is equal to area, which in this case is 10 square feet. The shading coefficient, which is 0.41. And the solar heat gain factor, which in this case is 160. Okay. And the units for the solar heat gain factor would be in BTUH over square feet. So these will cancel out, and you're going to be left with units of BTUs per hour. And when you multiply all the numbers out, it's 10 times 0.41 times 160. And we're going to come up with a value of 246 BTUs per hour heat transfer through the window at that particular time, just from the radiation. So this only includes the heat transfer from the radiation from the sun through this particular window. That doesn't account for the total heat transfer across that window, because we also have conduction that is going through that window that we have to add on top of the radiation heat transfer through the window to get the total heat transfer through the window. So to figure out the heat transfer by conduction through this window, we're going to create a couple more givens. Okay, the first given is the temperature of the outside is at 90 degrees Fahrenheit, and the temperature of the indoor space of the building is at 70 degrees Fahrenheit. So if you remember, the formula for conduction is Q is equal to UA delta T. So going back to this example, Q is equal to UA delta T, where U is right here for the window, 0.3. The area will be the 10 square feet, and delta T will be the 90 minus 70F. Okay, so we will end up with a Q of 0.3 times 10 times 20, which is 60 BTUs per hour. So the total heat transfer through this window will be the sum of the heat transfer from conduction plus the heat transfer from radiation. So in this case it's 246 plus 60, which is going to give you 306 BTUs per hour heat transfer total across that window. Okay, now we're going to do an example that's a little bit more involved. Okay, so in this example, we have a house, okay, and in this house, it's a small house. It has two people inside. It has a computer, some skylights, window, and also a door. The door, you're not going to see it in this picture, but let's say the door is here, and there's a glass portion in the door as well. So if you look on the right side, these are the givens for this example. So the outside air temperature is 90 degrees Fahrenheit. The indoor air temperature will be at 72 degrees Fahrenheit. That's what the temperature will be maintained at indoors. The wall height is 10. Alright, so it's this height here is 10 feet. The wall width is 20 feet. So that basically is the wall that goes into or out of the page, depending on how you want to look at it. Okay. Now the U value of the wall is something that we need to find out in the New York City Energy Code, because the Energy Code gives you a maximum value of U that can be used, or that's legally allowed to be used in New York City. And this information could be found in the New York City Energy Code that is available online. So it's public information. You could just go to the New York City DOB website, and under the code section you'll find New York City Energy Code. So in that code section they give you a table, which is these two tables here. So if you look at these two tables from the New York City Energy Code, you have on the table on the left, it's going to be the minimum R value method, and the table on the right is the maximum U factor method. And the reason for these numbers is because the New York City Energy Code wants to minimize the heat transfer, gain into a space or loss from the space to the outdoors, to minimize the heating and cooling load or energy usage of the building. And if you remember the formula, it's Q is equal to U A delta T, or Q is equal to 1 over R A delta T. So in order to minimize the Q, you want to keep the U value at a maximum, no larger than that maximum number. Okay, which is the reason why when you're considering the U value, the Energy Code gives you a maximum for that. And for the resistance, if you're trying to keep the heat transfer low, you want to keep the R value at a minimum, because any lower, when the denominator is getting lower, that Q will go up. So there's a minimum number when you're referring to the resistance value. Now in this example, we need to get the wall U value as well as the roof U value. So, and in this case, this is grade. Grade just means the ground level. So when we look for that value, we're considering this column here, the number 4 column, climate zone 4, which is New York City. So all this we don't really need to consider for New York City. And this column is all other spaces. This is group R, meaning residential group. And in our example, we're talking about a residential building, so we're going to use this column here. Now, this is split up into a couple of sections. One is the roof. Here is the walls above grade, which is what we need to look for. And in this example, we have a wood frame building. So we're going to look for this one here, wood framed, above grade. So the U maximum is 0.061. So here is 0.061 as the U value. Now we need to look for the roof U value. So that's going to be this top area here. And in this example, we'll say that we're not sure what the U value is going to be. So in those cases, we're going to pick the worst case scenario. Okay, and in this case, it will be the 0.035, since it's the highest one out of all three of these. Okay, so we're going to use 0.035. Alright. Now we have a people load of 2 people. So we go into this table here. This is the table that we use to figure out how much heat is being generated by the person. And on this column here, it's sensible heat. That's just the heat that the human is producing to raise the dry bulb temperature of the air. And the latent heat is the heat that is being added to the air through moisture. So basically from the human sweat evaporating into the air and adding moisture to the air, we're adding latent heat to the air. And the total of these two is the total heat generated by the person. And depending on the activity, there's different numbers for these two values. So if you look at the top, this is when the person is in a relaxed state. They're at a theater. The sensible heat is 200 and the latent heat is 130. As their activity increases, the sensible heat will increase as well as the latent heat. So if you look down here, the factory heavy work or gymnasium, the sensible heat is 510 and the latent heat is 940. In our example, let's pick a value somewhere in the middle. Okay, so we'll use the value right here. Somebody at a bank, for instance, and that value is 220 and latent heat is 280. So the total of that will be 500. Alright, and the units are right here, BTUs per hour. Next we have equipment load for the one computer here. And we'll use this table for that, these two tables here for the computer. Now if we're not sure what size computer it is, we always use the worst case scenario so that we size the HVAC equipment to handle that the maximum load that can be generated. So the worst case in this would be the 80 for a large monitor, and that's in units of watts. Alright, and for this computer, we'll also say that it has a laser printer. And for the printer, we're going to use the large office printer data. And we're going to use the idle wattage of 125. And the reason we're not going to use the continuous wattage is because when we're calculating the heat loss in a space, we don't want to use the maximum output that the computer is generating in order to figure out what size HVAC unit we're going to be selecting. And the reason for that is because, you know, it's gonna cause us to size the HVAC system too large for what the typical load is going to be, since that continuous wattage is not something that's occurring, you know, many hours of the day. It might just be for, 1 minute in a day or, 5 minutes. So we're going to use that idle wattage for this case. So that's 125. Okay, so we're going to add the two numbers up. So it's going to be 125 for the printer and 80 watts for the large monitor. And we can use the continuous wattage for the monitor just because, a monitor can be on, several hours in a day. So we're going to use that value. And total is going to be 502 watts. Okay. Okay, now we have some lighting in the space, and the general energy code says that the maximum is around 1 watt per square foot in a residential unit. So this is the value we'll use. to calculate the wattage produced by the lights. And if you look, this is the conversion between watts and BTUs. So 1 watt is equivalent to 3.41, so which means that when we do the conversion of the computer, which is 205 watts, we have to multiply that by 3.41 BTUs per hour per watt. So these watts will cancel out and you're left with 699.05, or let's just round it off to 700 BTUs. So that's 700 BTU per hour for the computer load. And for the lighting load, you could do the same thing. It's just 1 watt per square foot. And for this space, the square footage we have is going to be 20 by the length is going to be 30 times 20, so that's 600 square feet. Multiply that by 1 watt per square foot. And then we have 3.41 BTUs per hour per watt. So these cancel out, and you're left with 2046 BTUs per hour for the lights. So here we have 2046 BTUs per hour. Okay, now we need to calculate the heat transfer through the 2 windows at 10 square feet each. To do that, we go back to the general formula right here, which is the QASC SCL. Alright, and in this case we have this side is going to be designated as the south side. This side is going to be the north side. Okay, and the date and time of this example is January 21 at noon. So in order to get, first we need to get this value here, right, the SC value. And the SC value, we're going to use this information here. Okay, solar heat gain coefficient is 0.36. So 0.36 is the solar heat gain coefficient, and we need to do the conversion to get the SC value right here. 0.87 times SC is solar heat gain coefficient. So 0.36 divided by 0.87 will give you the SC value of 0.41. 0.41. Now the SCL value is the same as the solar heat gain factor, right? So at January 21 at noon, these are the values we're using right here. And the south side will be 254. So we have 254 for the SCL, and the area is 10 square feet. Okay? So this will give you a value of 10 times 41. 104,140 BTUs per hour. So we have 2 at 140 BTUs per hour for the window. We also need to calculate the conduction through the window. So what we just calculated was a radiation heat gain through the window. Now we need to add that to the conduction. And the conduction formula is Q is UA delta T. And the U for this window is 0.3. The area is 10. And the delta T is going to be 90 degrees minus 72 degrees. Okay, and that's going to give you 54 BTUs per hour. Another table in the New York City Energy Code gives you the maximum U factor as well as the solar heat gain coefficient for fenestrations. Fenestration is just another name for glazing, which is also another name for just a window. Okay, so the window that we used, let's just determine if it actually complies with the energy code. So if you look on the top, vertical fenestration, the U factor, now this column is anything above 95 feet, and this is below 95 feet. The numbers are very similar, so in this case we're going to use this one, below 95 feet. And the window in this case will say it is a metal framing that's operable. So the window has metal frames, and it can be opened and closed. Used was 0.36, so we actually comply with the energy code requirement of a maximum of 0.40. We also need to look at the solar heat gain coefficient. Okay, now this term here, PF, stands for projection factor. And the projection factor just means some sort of overhang on a window. So let's say this is the window, and you have some sort of overhang over the window. So the projection factor, if it's a smaller number, if it's 0, it means there is no overhang. As the projection factor increases, right, as it increases, then that means this projection factor is coming out further and further out, providing more of a shade from the sun to the window. So as you have more shading, the maximum U value can increase. But in most of the load calculations, we're going to use the worst case scenario, which is that there is no shading available. So in that case, the projection factor we would use would be this one here. And the maximum U value we are allowed to use would be 0.36. The maximum solar heat gain coefficient we had for the window was 0.36, which complies with the energy code maximum U value here. For the skylight, let's assume that the architect has never given us any type of model number to use for the skylight. When calculating the heat transfer in the building, we are going to use the U factor and the solar heat gain coefficient that is allowed per energy code. We're going to use a U factor of 0.48 and a maximum solar heat gain coefficient of 0.38. So here in this case we got the two skylights, alright? So the maximum U value was 0.48 and the maximum solar heat gain coefficient was 0.38. So U factor 0.48 and solar heat gain coefficient 0.38. Okay. Now the skylights, since we have each one at 20 square feet, the formula was Q is equal to A shading coefficient times solar cooling load. And if you hear solar cooling load, again, another name is solar heat gain factor, which is in this table. And for the dates and time we are considering for this example, we have to look at this value here, horizontal, right? And that value is 133. So 133 is the value for that, and SC times 0.87 is equal to 0.38, which is the solar heat gain coefficient, which was this formula here. To get SC, the value is going to be 0.44. So plugging all the values in, we get 10.44 and 133. So the value of Q using the 20 is 1170 BTUs per hour for the radiation heat transfer through the skylight. And there's two of them, so we have 1170 BTUs per hour. And we also have to add the conduction heat transfer through the skylight. So the formula for conduction again is Q is equal to UA delta T, where U is the value that is allowed per energy code right here. Alright, the 0.48. That's the maximum U value, so we're going to use that. And the area is 20 square feet for each skylight, and the delta T is the outdoor temperature minus the indoor temperature. So 90 minus 72 is 18. And the answer for that is 172.8. So I'm going to round that to 173 BTUs per hour. Okay, next we're going to calculate the heat transfer through the door. And the door, we are going to first calculate the conduction heat transfer through it. So U, A, delta T. And the U, we're going to use the maximum allowed per energy code. And that's going to be in the table over here. And we are above grade. And to get the maximum U value that we are allowed to use based on the New York City Energy Code, we're going to go back to the table here and go down here. You see here it says opaque doors. Opaque just means no light is able to penetrate the door. So we're going to use that value for swinging door. And again, New York City is climate zone 4 and we are in group R. So we're going to use a U value of 0.5. 0.5. And we need to get the area for the opaque portion of the door. So the door is 21 square feet total. And there's a 2 square foot window within the door. So the opaque portion of it is 19 square feet. So we're going to use 19 here. And delta T again is the outdoor air minus the indoor air, and that is 18. And that's going to give you 171 BTUs per hour. Now we're going to add the radiation heat transfer as well as the conduction heat transfer through the small fenestration in the door. Okay, now we need to get the conduction heat transfer through the fenestration in the door, which is 2 square feet. So we get Q is equal to U, and the U of the door fenestration, we need to go back to this table to get that value, and it's under here, entrance door, and it is 0.77 for the U factor, and the area is 2, and the delta T is 18, which equals 27.72. I'm going to round that up to 28. So the total conduction through the door is going to be 171 plus 28, which is going to be 991. So it's going to be 200 BTUs per hour. And now we need to add the radiation heat through the window portion of the door. Okay, now to get the radiation heat transfer through the glazing of the door, we use that formula again, which is Q is equal to the area times shading coefficient times the solar cooling load, or the solar heat gain factor, which is here again. Alright, so the area in this case is 2. Now to get the solar heat gain coefficient for the window portion of the door, we go back to this table here, C402.4, and we use this part of the table, and again we use this 0.36. And we're going to assume that there is no projection factor or any type of overhang that's providing shading to this window portion. So we always use this value here, 0.36. And if you go back to get the conversion, it's 0.87 is solar heat gain coefficient. So you divide this by 87. And then 0.41 goes in here. And to get this value, solar cooling load, again, solar heat gain factor is another term for it, we need to use the right orientation. In this case it's the north, and the value is 20. And that will equal to 16.4. I'm just going to round that to 16. Okay, so the total for the door is going to be 200 plus 16, or 216 BTUs per hour. Going back to the wall and the roof, we last calculated the U value only. Now we need to plug that value into the formula to get the conduction rate through the wall as well as the roof. The formula is going to be QUA delta T, where the area is just area of the wall, so that's subtracting all the window areas. So if we're going to work on the south side wall for now, we have a height of 10 feet and a width of 20. So that's 200 subtracted by the window area, which is 10. That's going to be 190. And we have an equivalent wall area on the north side, so that's going to be 190 plus 190. And then we have a wall section that is facing perpendicular to us from the page, and that's 30 feet by 10, which is 300. And we have an equivalent area on the opposite side, so that's another 300. And then the total of that will be 980 square feet. and U is 0.061 times 980 times delta T, which is going to equal 1076 BTUs per hour. Okay, now we need to calculate the conduction rate through the roof, just like we did for the wall. Now the formula is QUA delta T, and the wall, the roof U value is 0.035, and the area is 30 times 20, so that's going to be 600. And we need to subtract the skylight areas from that roof area. So the skylight, we have 2 skylights at 20 square feet each, so we're going to subtract 40, and we're going to get 560 square feet, which we're going to plug into here, and delta T is 18, and that's going to equal 353 BTUs per hour. So now that we calculated the heat transfer through the building envelope, through the walls and the roof, and also we calculated the internal heat produced from the lights, people, and the equipment, now we can total all of those up to get the total heat gain into the space. So we're going to start from the top and just add up all the different components. Alright, so for the wall it's 1076, the roof is 353, the people load is 2 people at 500 BTUs each, the computer load including the printer was 700, the light load is 2046, the window there are 2 each at 1041 plus the 54. The skylight there's 2, 1170 plus the 173. The door we have 1 at 216, and summing all this up we get 10,267 BTUs per hour. And if we want to convert this to tonnage, it's 12,000 BTUs per ton. Multiplied by the 10,267 BTUs per hour. The BTUs will cancel out, and we're left with 0.86 tons, and that would be the total heat generated in this space at this given time. Now if we were to select the HVAC unit, we would select the next standard size, which most likely will be a 1-ton unit for this space. That concludes this lesson. Thanks for watching to the end.